Yeah. Is it those we had
All right, starting with number one. Okay, so creating the slope field, all we're doing is identifying the order pairs. So I have 9 order pairs here. Taking each of them, inserting into the derivative equation, into your differential equation. Getting a number in return and representing those with either positive slope, 0 slope, negative slope, or slope undefined. And slope undefined would be if it ends up being a 0 in the denominator, and you can leave that order pair empty. Okay, so it really doesn't matter how steep you make your positive or negative slopes, as long as you can represent them in one of those 4 categories. So for instance, if I enter 2, 0 in for x, 2 will give me 8. 8 minus 3 is 5. 5 times -1 is -5. So I have a negative slope representing that order pair. Any questions of those? All right, part B. Find a particular solution for y equals f of x to the given differential equation with the initial condition f of 0 equals 1. So we're going to work towards separating the variables. Okay, so I'm going to go through my method of working through that. Okay, so anytime you see parentheses provided for you in a differential equation, they're asking you to solve it. Leave those parentheses there. The parentheses are there to help you separate the variables a little easier. If you don't want to expand through and use those parentheses, then the x and y's are end up being even more merged together. Okay, so cross multiply. So when you cross multiply, you have your dy dx's locked in. Those are in the right places. The only thing you have to consider, maybe the x's and y's are not quite yet separated. That's the case here. Let's say the 2y minus 1 is out of place. You have to divide both sides by 2y minus 1. Okay, so now that the variables are separated, I can drop those parentheses if I wanted to. Left side, I'm going to go through a little bit of use substitution. The right side, these are separate terms. These are nicely both set up for power rule. Pull the 1/2 out in front. apply my antiderivative rule. Bring in the original variable. Okay, and then left side required a lot more work for me to get it to antiderivative. The right side, I can just go through power rule. Okay, so I'm done with the calculus once I get to this stage. Okay, any questions so far? Now, as soon as your plus C shows up, you're more than welcome to plug in and solve for C. I'm going to wait a little bit longer. I feel like I can get rid of the 1/2. I can take get rid of the natural log, solve for Y first. But really, it's really up to you in terms of where you want to solve for C. I'm going to not get it until I feel like it's an easier equation before I solve for C. But basically, you can solve for C anytime. You can wait till now, do it now, or wait until the very end, or sometime in the middle. As long as you keep track where you made your substitution. I'm going to get rid of the 1/2 first, multiply through by 2. So 2/4 becomes 1/2. 3 times 2 is 6. And then 2C is the same thing as just C. Just clean that up to just be C. Okay, I want to solve for Y. Y is stuck inside the natural log, so I'm going to raise both sides with E as the base. E and natural log cancels out. And all this is raised to the exponent. I'm going to work towards separating that C away from the rest of my variable expression. But we got to change that operation, right? Plus becomes a multiplication here because I'm bringing this down. E to the C is just C. Pull that C out in front, drop the absolute value. I'm going to solve for Y here, so I'll add 1 to both sides. Divide by 2. Divided by 2 is the same thing as multiplying by 1/2. Now 1/2 C, we're basically multiplying 1/2 with a constant, so I can drop the 1/2 because it's attached to the C here, so I don't need that one. So this is as cleaned up as I can get it. I have Y by itself. I feel like this is the easiest place for this problem for me to solve for C. So my order pair is 0, 1. I can isolate C and solve for C. E to the 0 is 1, so that drops out. I have 1 equals C plus 1/2. Subtract 1/2 from both sides, C equals 1/2. So here's my specific equation. Replace C with 1/2. Sorry, C equals 1/2 now. Place 1/2 in for that C there. All right, that's part B. Question?
The worksheet. Okay. Yeah.
Okay, so now part C says find the equation of the line tangent to the function at the point where x equals 0. And use it to approximate f of 0.2. Notice the direction here. It says find the equation of the line tangent. So that means ultimately we need a linear equation. We're not going to be using any of the functions that we created at the end. This is a tangent line here. It's a line, right? So we know ultimately I'm trying to get it into this form, right? That's my tangent line equation here. Okay, so I need to find a replacement for x1, y1, and for my slope. Right, they give us the order pair. Order pair is 0. In this case, they gave you the order pair 0, 1, but if they give you a different point, you can still find that other order pair by using this equation. Okay, but in this case, the order pair is given to you here. Slope comes from your derivative equation. Your derivative equation is your differential equation. So we just plug that 0, 1 into this derivative and get that slope. This just means I'm about to insert 0 and 1 into my differential equation. So I get -3 here. -3 times 1 is -3. There's my point. There's my slope. So I can do point slope form. Do a little bit of cleanup here. I'm just going to add that 1 over to get y by itself to get myself ready for the next stage. Now that I have my line tangent, I'm going to do my linear approximation, which is approximate f of 0.2. That just means inserting 0.2 and replacing x of my tangent line equation. You can leave it in this form, or you can plug in the calculator and get that decimal value. Either is fine. Okay, questions? All right, number 2. Okay, so we're looking for a u value. This is too complicated for any one rule to handle. So this we can go through cleaning the denominator, get a parentheses to show up, and then picking out the u value from the denominator. Okay, derivative of 1 is 0. The derivative of e to the u is e to the u times u prime. In this case, it'll just be 2e to the x times 1, which I can just drop that 1. Not going to make a difference. Okay, cross multiply. Make my substitution. Okay, so we need the x's to go away, and they do. Pull the 3/2 out in front. But take a look. This is a cleaned up version of the problem, but what rule do we use to handle this problem? Power rule, right? This is not natural log. I know you're seeing that u in the denominator. Sometimes you're tempted to go through natural log, but natural log is only if it's u to the first power in the denominator. If it's anything else, we gotta bring it up to the top and go through power rule. So now this is all nice and set. Go through power rule. There's no plus c because we're dealing with bounds. So I'm going to clean this up, bring my original variable back, and then I can work in my bounds. 6/2, which is 3. 3u to the 1/2. I'll bring my original u, my original x variable back. Now my bounds are ready to be used. Okay, upper bound first. Minus lower bound. Careful. A lot of times 0 does wipe out the entire expression, but in this case, we got to double check everything here. There's going to be some leftover here, even though that we see a 0 there. Okay, there's not much that we can clean up. It's not going to clean up nicely, but I can do a little bit of work here. 2e to the 0, same thing as 1. I can merge that to be just 2, or sorry, e to the 0 is 1, so 1 plus 2 is 3. Not much more we can do, but that's just a number. Okay, this is a numeric value, represents the area under this graph. Okay, next page.
Sorry, can you go over the bounds one more time?
Right, so once we take the antiderivative, and normally you would get to this point, right? And normally you would say plus c. But because there's bounds involved, you're not going to use the plus c. Instead, you're going to plug in the bounds. So upper bound gets inserted first. The 3 goes in for the x. Then we do minus, and then the lower bound gets inserted in for x.
Yeah.
And then we just try to do a little bit of cleanup. Yeah, simplify and get that. We know that's just a number, and that number represents the area. Okay, number 3 word problem, the rise in population of a town. I'll use P to represent population, but it says the rise in population. So you know that's a rate. So I'll say P prime is directly proportional to the number of people. So P prime equals KP. So anytime we see this relationship, we know it's going to end up being Y equals CE to the KT, or in this case, P is equal to CE to the KP. Technically, we're solving the differential equation, but we know this is always going to lead to this. Okay, so we're going to skip the calculus and we're just going to work from this equation. Okay, so population doubled in 50 years between 1920 and 1970. 1998, population was 500. What's population in 1920? So we're going to solve for C, find K, create the this particular solution, and then we're going to use this particular solution to help us make that prediction. All right. So I like to create order pairs. Time is my independent variable. Population is my dependent variable. So I like to find the earliest time and use that to represent my earliest year. So I'm going to use 0 instead of 1920. It's just easiest if I can, anytime I can involve 0. So know that at time 0, there's some population. I don't know what that population is. That's what I'm looking for. So I'm going to say 0, comma C. Right? I know there's a starting population. Normally that's what we start with, but in this case, this is what we're looking for. Okay. Population doubled between 1920 and 1970. So that means 1970 is 50 years later. What's going to happen to this population? Let's see. Whatever that population is that we're looking for, we know it's going to double. And then the population was 75,500 in 1998. How many years after 1920 is that? 78, right? So we know 78 years later. Okay, so normally we would plug the first one in and solve for C, but in this case, we don't know what C is, so we're not going to make any progress. Let's start with the second order pair here. I think this was going to help us get to that K value, but let's just insert 50 in for T and 2C in for P. See what happens. So what's nice about this here? What happens? C's what? Cancel out. So I can just basically work towards solving for K here. To bring that K down, I can involve natural log. Bring that 50K down. Natural log of B goes away. Divide 50 from both sides. Okay. Put this back into your equation. Update it along the way, and then we can continue to make progress. So again, this 0C is not going to help us out, but let's see if we can insert this third order pair here. So imagine putting 78 in for T and 75,500 in for P. Then the only variable remaining is C, so we can use this third one to help us isolate C and solve for C. Okay, so now all we need to do is find what this number is and divide that number over. 75,500 divided by this will give us our C value. So this divided by this mess of a number, self-receipt. Okay, next up, number 4. Match the differential equation with the slope field graph to the right. So I like to always look for 4 things when I'm looking at a slope field to help me narrow down my options. Where do I see slope 0? Where do I see slope undefined? Where do I see positive slope? And then where do I see negative slope? So slope 0 and slope undefined is kind of hard to pick out because they could be hiding behind the axis and we don't really know. So sometimes we can't rely on the axis. It could be either hiding information or kind of obscuring information. So we don't see any slope 0, slope undefined outside of potentially the axis. But let's look at where we see positive and negative slopes, right? So positive slope, I see positive slope all within first quadrant. I see positive slope all across the fourth quadrant. Negative slope, I see negative slope second quadrant and fourth quadrant. Or sorry, second quadrant and third quadrant. So I can just eliminate some of the wrong ones that I see, right? So if I imagine, if I plug in 1, 1, I'm getting a positive, I should be getting a positive number. There's no way that this will give me a positive number in return. So this is out. X squared over Y squared. How do I know this is not right? This is always going to give me 1 in return. Positive, right? Any order pair you plug in, it's always going to get squared. It's always positive. So, but we do see some negative slopes here. So this can't be right. I'm getting negative slope at second quadrant. So let's say like negative 1, 1. Yeah, that's not going to help me narrow down anything here. Quadrant 3, negative 1 should give me a negative slope. This one is out, right? If I plug negative 1, I'm getting negative over a negative, which is positive. It's not consistent with what I see here. Okay, so I'm down to 2 here, either x over y squared or y squared over x. Okay, here I see that as I get further and further up, my slope is getting closer towards 0, right? So I know that as my y value is increasing, it doesn't matter what the x is. Whenever my y value is increasing, it's always getting closer to 0. So for instance, this order pair here, 110, I should be getting like a very, very small positive value. right? So if I plug in 110 in here, I'll get 100 over 1, right? And that's obviously not a slope that looks anything like 100. That's closer to a 0. If I put something in here, 1 over 100, that's basically close to 0, but still positive, but almost flat. So we're just kind of looking at different order pairs. Once you're down to 2 options, you're kind of just looking around to see what can you do to help you narrow down your options, even though we don't know the exact slope at these particular points. But you do know what a very steep positive slope looks like and what a very gradual slope would look like. Okay, number 5. Okay, we have rules for both of these problems here. We can treat them separately because they're separated by either plus or minus, but we got to go through use substitution for both. Sine of u is just one of the original ones. So integral of sine is negative cosine. Integral of cosecant, this is one of the newer ones involving natural log. So we really just treat this like 2 separate problems, right? We got to go through use substitution for the left side, use substitution for the right, and then apply the rules for them accordingly. So I'll show the work here. I'll walk you through it. Okay, so focusing on my first term here, my u value is pi x over 3. I'm trying to find a replacement for dx and try to get all that cleaned up. So u is pi x over 3. Think of this as pi thirds x. And that's just the coefficient in front of my x. So the derivative of pi over 3 times x is just pi over 3, right? Just that number in front of the x. Cross multiply. Pi dx equals 3 du. Solve for dx. Dx equals 3 du over pi. Make that substitution in for your original problem here. So sine u times 3 over pi du. Pull the 3 over pi out. And now I'm ready to apply my antiderivative. So I'm going to save this until I get the right side, the other term ready. Okay. Next term, u equals 5x. I'm going to replace that 5x and the dx. U equals 5x. Du dx equals 5. Dx equals du over 5. Push that 1/5 out in front. So now both terms are ready for me to apply my antiderivative rule. If I'm keeping track of my coefficient, that's going to hang out in front. So now I'm here. Sine u becomes negative cosine u. Cosecant u becomes negative natural log cosecant u plus cotangent u. And then once I apply my antiderivative rule, I bring back my original variables. So for the first term, I bring back pi x over 3. For the second term, I bring back 5x. Do some cleanup here. The 2 negatives become positive. Okay, next up, number 6. Okay, so one thing that I noticed with number 6 is that there's a significant gap between my highest exponent in the denominator and the highest exponent in the numerator, right? There's that gap of 2 or more. We know anytime we see that gap, we're looking to use our trig to help us narrow down that option. But I see that this form of is going to take on, well, I know it's either arcsine, arcsecant, or arctangent. It can't be arctangent because that's the square root. And also, this feels like more of an arcsecant because my denominator has variable first. So it looks like more like a u squared minus a squared, and that coupled with this in front looks more like a arcsecant, right? So we're targeting towards that arcsecant rule.
Wait, how did you do that?
So we have 3 rules available to us. It's either du over a squared plus u squared, du over square root of a squared minus u squared, or du over, right? And then we know it's one of these two, but we see what comes out first is that variable. So that variable is being squared and being positive first. So it's better fit with that arcsecant. Okay, so we know this is what we're trying to work towards. Okay, we're trying to make this problem look exactly like this rule. Then we know we can apply it. All right, but we know we have to do some work with our inside our radical because these are not the correct u and a values. We got to get it into the proper form. So this is how we're going to do it. Okay, so what can I put inside this parentheses so that when I square it, I get 16 next to the fourth? 4x squared. What can I put inside here so that when I square it, I get 7? 7, because I don't want to change my overall value, but I do want this proper form. Otherwise, I'm not able to pick out my correct a and u value. Now I'm going to leave this. Well, we know that's our u value already, so we already have this 4x squared sitting out here. That's good. So I'm going to make my substitution here. I'm going to replace these 3 terms. My u value is 4x squared. My a value is root 7. Derivative is 8x. Solve for dx. Okay. So I'm just trying to get myself closer towards this rule here. I'm going to replace my denominators with all the things that I found. Replace dx with du over 8x. Now, do the x's go away? Yes, right, that's a good sign. But we do need to keep track of what? 3/8, right? So now that I have a perfect match, I'm convinced that I can apply my arcsecant rule. So now I can jump directly to my arcsecant rule. So 3/8 comes first, followed by the 1 over a, arcsecant, absolute value of u over a, and I can replace my a's and u's with what I had in my problem originally. Or we can pull this together and just put it under one fraction, 3 over 8 root 7. But no need to rationalize the denominator. You can leave radicals in the denominator. Okay, number 7. Okay, so what gives it away that this is going to be our trig integral problem as well is because you see the highest degree in the denominator is 2, the highest degree in the numerator is 0. There's a gap with the degree in the denominator being higher. It's more than 1 is 2 or more. So we know that gap requires our trig to help us get that to allow for this to work. Okay, we don't see a radical in the denominator. That's an easy find. We know it's going to be an arc tangent. We're working towards this rule, but this trinomial doesn't allow us to quickly find the A and U values. So we do need to do something a little bit extra to get this trinomial into a binomial squared, or the sum of 2 binomial squares. So the method there is completing the square. Which is a method to get this trinomial to be in the proper form without changing the overall value that we see in the denominator. So we have a plus space and a minus space to ensure that whatever number we add, that we immediately subtract so we don't change the overall value of the expression. Now what goes inside the space is this formula, b over 2 squared. What's my b value? 16. 16 over 2 is 8. 8 squared is 4. This is going to factor nicely for us. Multiplies to be 64, adds it to be 16, which is going to be 8 and 8. And then 67 minus 64 is 3. Okay, so we're getting closer towards the proper form that we want. So I have x plus 8 quantity squared, plus I also need another quantity squared to get that proper form. My overall value is 3, but what can I insert inside the square, inside the parentheses? What squared equals to 3? Root 3. All right, so double check it. Root 3 squared is that. This squared gives me that. So I have my u and a values sitting in front of me now. Go through u substitution. And I'm trying to get my problem to look exactly like this. If it does, I know I can apply my rule. I'm going to pull the 7 out in front. I know that I can just sit out here in front. ds gets replaced with du. Perfect match. I can apply my rule now. The 7 is going to hang out in front, so that's going to come out first. Okay, number 8. All right, can you tell by looking at this problem what method is involved to find the antiderivative or to first set up a problem? It is either synthetic or long division. I know there's a gap here, but it's in the other direction, right? This is if the degree in the numerator is the same or higher in the numerator, then we have to go through long or synthetic division to rewrite the problem to help us create an easier version of the problem. So we can go through synthetic here. So set x plus 1 equal to 0. I get -1. Create my half box. 2 represents my x cubed. But I have a lot of what? A lot of zeros, right? Because I need a I need a placeholder for every degree that I'm skipping over. So I have a degree 3. I have a 0 for x squared. I have a 0 for x. And then the -5 is for the constant, right? I have a column for x cubed, column for x squared, column for x, and column for my constant. Right. So we always bring down the first number without changing anything. Now we start multiplying and adding. So 2 times -1 is -2. -2 times -1 is 2. We add 0 plus 2 is 2. 2 times -1 is -2. We add -7. If you don't see a 0 at the end, you know that's your remainder. And then you have to assign variable x degrees to each term. You know that you're starting off with x cubed, so you're dividing by x, so you're going to drop by 1 degree. So this becomes x squared. This is x. This is the constant. And this is the remainder. We haven't solved anything yet. We haven't done any calculus yet, but we've created an easier problem for us to handle. Power rule for each of my first 3 terms. Last term, I can go through a little bit of use substitution, but it's going to be a natural log problem. Going to get that out of the way first. Okay, so I know that's the result of my last term. Apply power rule for each. Normally I would do a plus C, but why do I not do that? There's bounds, right? So at the very end, instead of putting a plus C, you'll do a 1 and 3. Okay. Upper bound first, followed by lower bound. Not to clean anything up, just leave your answer all in that mess. That's perfectly fine. Upper bound. In for my expression here, I get 2/3 3q minus 3 squared plus 6 minus 7 natural log actual value of 4 minus big parentheses, lower bound, insert for each of the x's. You leave your answer unsimplified. This is also acceptable in the AP exam. Okay, this one's a little bit tricky here because we really need to bring this 3 down to make it easier. So I would actually do this. I would bring that 3 down in front first, and I will give you a problem that looked more like this to begin with. Right, so that 3 will come down because it's not part of the x. But if you had this as your starting problem, we know it's going to have to be used substitution because this is too much for any one rule to handle. Any guesses as to what the u value could be? On next, right? Because this will handle this remaining x nicely for us. Okay, so we go through our use substitution steps. Cross multiply. I'm going to pull that 5 and 6 out in front since this is going to hang out. Replace the dx with x du. There's an x that remains in the denominator. That's perfect. The x's cancel out. This ends up just being a natural log setup for us. Okay, 5/6 natural log absolute value of u plus c. And replace the u back in terms of the original variable. Okay, I'll walk around, see if you guys have any individual questions.
That's like very simple. It's created a very simple, so we just created. So just created. Whatever time. We know he's been so. Oh, I see what you're saying. No, I see what you're saying. Yeah. One grade up. So it's basically. I can do everything while I don't want to like start. Once I'm doing it, that's deciding if I. No, it's just, I love the, this. Wait, that was, this was. I didn't work. Oh, it's the first one. Right, so please get these help, obviously. I don't know. I don't see how they do words. Guys are sitting next to you, you're just looking at them, you're like, we're stuck in the thing. I'm still. You'll be fine. Yeah. Her eyes, like, I can stop. I'm like, I can't do that. My mic dropped. I know. No, not. But. And then what they're saying. Oh, you know, he does the part. Whenever he does like the guitar, he comes back to the sound. Okay. That was they messed it up though, so. You're changing something. Like the whole song is like, but I love it. It's like, and this is just funny. I have to tell. He walked in his driveway, and then he like jammed on his Instagram, and then leaving until you go out. But like, if we get you now, the party's out of town. Like,
we'll wait to like submit your code until Saturday, so then your partner, you guys could stay in. And then the dude's like, I'm not football out. He wasn't even at his house, like he didn't even check, so now he knows exactly who it is.
I left five.
Yeah.
Here, and I was like, honestly, if somebody's waiting outside my house at 5, it's gonna be like, good for them. Like,
Yeah.
I would be like,
I didn't make sure he was home, so he just texted us, like, a threat. I need to do that.
It's like this whole bunch of we just like go paradoxical. Yeah. Go like no.
Yeah, but I think that it's fine this week. Yeah, exactly.
Yeah. I just don't want to see.
I just want to time. I like mine to get ready, but I feel like it dies really quickly. Like I feel like everyone's so invested in this one.
Like, yeah, I don't know how to explain it. It was like really chill last year and like fun. And then now it's just like.
Oh my gosh. No, you have to hear how Jack got. How Jack got out yesterday. I watched it happen.
Cut out two.
You did too?
Yeah. All, partners.
You guys are out. I was watching it for the last week. He was playing. Jack started to yell at me. Funny times.
No one's expecting it. They just like never came.
Yeah.
Did they go to Owen?
All I know is that we're.
They don't know who
They
they
just gave up.
They just didn't come.
But I get it.
You did not, you don't have it.
Yeah. But I didn't know.
That's what takes.
Which means I still need to.
Don't look at it. Well, apparently, you said it didn't matter, so it's you, like, well, look at. Yeah, but first, trust is first, that's your A value, so it's A is first. It's gonna be. Yeah, so this is gonna be outside. But that's what I did, you over A. Guys, I need all your book bags up front. Oh, yeah. I could.
If I. Yeah,
Yeah.